Hello students, in this video we are continuing with fluid dynamics, right? Properties of matter, fluids and fluid dynamics. In today's topic we are going to discuss about streamline motion and turbulent motion of the fluid, or in generally streamline flow and turbulent flow. Now what do you mean by streamline flow? Let us take for example a river. Okay, in a river the water is flowing. Okay, now let us assume a particular set of water line. Okay, we will assume a particular line. Let us say in this I assume this line. Okay, the water is flowing like this. Let us say, let me erase all the other points here. Okay, yeah, I am assuming one particular line, that water is flowing, that particular line, and I am going to discuss about how streamline flow and a turbulent flow can be. See, in a streamline motion, let us take there is a point here, right? And let us say this point is A. Now what is the direction of the liquid flow? What is the direction of the velocity of the liquid? You can draw a tangent at this point, right? And this velocity, we can say velocity at the point A, and this is a vector quantity. Now let us assume the particle is moving from here, it comes to this point and it is little up. So again draw a tangent like this, and this velocity of the particle at this point B, VB, we will say. Now we will assume, let us say another point here, let us say call this point as C. At this point again let us draw a tangent, okay, and velocity at this point is VC. You see, I have taken a particular line of liquid flow, only a particular single line I have assumed. In that I am seeing at this point A, the velocity is VA. Some other point B, that is velocity B, and some other point C, okay, it may go like this, right? Velocity, it can go something like this, let us suppose, okay, that is velocity C. According to streamline flow, whatever the particle is coming to this point, right, A, they all should have the same velocity. See, the particle which is coming from here, the succeeding particle, let us say this is particle is X is here, and another particle from here is coming Y. When Y comes to the point here A, where the X was there, it should have the same velocity. That means the velocity at any point should be constant. Now velocity can be different. Velocity at this point can be 20 meter per second, and the velocity here can be 25 meter per second, and the velocity here can be 15 meter per second. The velocity can be different, but at a particular point the velocity should remain constant. The successive particle should have the velocity of the previous particle. The particle which passed through this point, the same velocity it should possess. And such a motion is called steady flow. It is also called steady flow, or also it is called uniform flow. And this is generally termed as streamlined flow. Streamlined flow. So what is the condition? That in a particular point the velocity should be constant, and all the particles coming to that point should possess the same velocity, and different points can have different velocities, and that is called streamline flow or steady flow or uniform flow. Usually we draw it just like this, you know, they are all parallel to each other. Okay, this kind of motion you refer to as uniform motion. Right? Suppose, contradictory to this, if the velocities are changing at the different points, then what will happen? The motion will be haphazard or zigzag. It will be moving zigzag motion. We will say zigzag motion, or it will become haphazard. Haphazard. The flow will be haphazard. Everything depends on a limiting value of the velocity. The velocity should not exceed a particular value, and that velocity is called critical velocity. The velocity should not exceed the critical velocity, right? This is the limiting value. If it exceeds that, then it will be called turbulent flow. Turbulent in life, we say turbulent times. What is the meaning? Corona now is there. Everybody, people are suffering. There are people who are not having job. People are having a financial problem. People are having health issues. These are the turbulent times. From Corona started around 2020, the early time to 2022 with the 3 variants. These are the turbulent times where life is getting scattered here and there, and we are thrown here and there and zigzag. Our mind is thinking this and that, and it is haphazard. People don't know. They go to this job, they go to this job. Sometimes lockdown is there. So these are called turbulent times, right? And it will be something what is happening now. For example, in a river, if the river is flowing smoothly, right? It is going very smoothly, right? That time you will have steady or uniform flow and streamline flow. But if there is a flood, let us say, in the flood time, what will happen? The water is gushing out. The water is coming with the different velocities. And that time, it will be zigzag and it will be haphazard and it will cause swirls, right? Circular. See, water is flowing like this, right? It is coming in different ways. It will cause swirls like this. It will cause circular motion. And that is called vortices. It is called vortices. We can call it vortices. Let me check the spelling here. I have written a point some here. Vortices. It's called vortices. So, what is a vortice? I will show you in a different and easier way to understand. Yes. Vortices. See, let us say, for example, we are talking about normal river is flowing. Yes, the normal river is flowing, it's all fine. Okay, it is having somewhere some problems. Otherwise, velocities might be different at one point to other point. Yes, you take for example Ganges. Ganges in Banaras Ghat or some other Ghat, the velocities will be different. That's okay, that is not a problem. But at a particular point, the velocity should remain same. At that particular point, whatever the water molecules are coming should have the same velocity. That's fine. It can be x value here, it can be y value here, it can be z value. But you will see that if it is flood, it is having flood, in some time you will feel a stick is being placed, and that stick you will find that circular, it will be like this, it will be forming. These are called vortices. Whirlpool, we say whirlpool, right? You know this washing machine, Whirlpool washing machine. It's just things it like this, you know, it just rotates it like that. So like that it will be forming, yes, and that time it will be deep inside, and this kind of motion is turbulent flow. Yes, and you will find that like that. That's called turbulent flow. In order to make you understand in another way, I would like to give an analogy, right? One analogy I will try to give. For example, on January 26th, Republic Day, and after that we had beating of the retreat, right? That's called beating of the retreat. Beating of the retreat. Okay, what has happened here? Soldiers make different formations and sing songs and play music. That time when the troop is walking, you'll find that all the troop members, right, left, right, left, left, right, left. When they go like this, they all will go with the same speed. You see, left, right, left, left, right, left. They go with a particular velocity, speed, particular march. They will march with a particular speed. Now they all take a turn like this. When they all take a turn like this, what will happen? You know that when it is turning, the velocity is going to change. But when it changes, the velocity again will have, all of them will have same velocity, uniform velocity, so that again the motion will continue, and that kind of motion you call it as uniform motion. The velocity at this point will be different, the velocity at this point will be different, so it can be, and this kind of motion is called streamline motion or uniform motion or steady motion, whatever the name we can give. Now I am going to discuss about something called laminar flow. Laminar flow. Now what is this laminar flow? We assume, I said to you before also, when we take a beaker and when we draw water in terms of dotted lines like this, right? See, why are we drawing in dotted lines? Why don't we draw? For example, you take this beaker like this. Yes, water is there. Why don't we draw something like this? Why don't we draw like this? No, we assume that they all are laminar. Laminar means like a sheet, right? A sheet is here. Here, sheet of water is going. Right, another sheet of water is there. Based on that only we discussed the viscous flow, the friction between the layers. We discussed all that, assuming that the steady flow, the streamline flow is basically laminar flow, where it is a lamina. Lamina is a sheet area we considered, right? And we can use it like this. Yes, different layers are moving. With these layers between them there is a liquid friction we discussed, and this flow is called laminar flow. Laminar flow will be there only when the velocity is less than the critical velocity, the limiting velocity. If it exceeds, then the layers will not be there as it is. They all will get mixed up, intermixed, and it will not be a laminar flow, and it will not be a streamline flow, it will not be a steady flow. Now, what is our aim is to derive an equation for the critical velocity. Now, the discussion what we are going to do is to derive an equation for critical velocity. Critical velocity. Okay, first and foremost, we are talking about a liquid. Liquid is flowing. Right? Now what are all the factors on which the velocity of the liquid will depend on? We will first find that out. Let us say that the water is flowing in a tube. Okay, that will be better that we can discuss with the help of a tube first. In a tube, water is flowing. In a pipe, water is flowing. On what factors the velocity will depend on? This is for the first discussion. Water is coming like this and it is going out like this, right? Non-stop, it's continuously moving. I have taken here laminar flow, right? Steady flow and streamline flow, right? The critical velocity may depend on the density of the liquid, rho, density of the liquid flowing. Water, 1 gram per cubic centimeter. Oil, the value will be different. That it depends on density. Second, it may depend on the coefficient of viscosity, eta. It may depend on coefficient of viscosity, which is liquid friction, right? It may depend on liquid friction. Third, where is it flowing? It is flowing in the tube. So let us assume that it depends on the diameter of the tube which we have taken. So capital D. So these are the factors it depends on. Now we are going to use dimensional method or dimensional approach so that we can solve this easily. Now dear students, you will understand In the second chapter, units and measurements, when we did dimensional method, some questions we have to wait till now. Why? Because now we have introduced the coefficient of viscosity. You should know now what is coefficient of viscosity and what is its dimension. Okay, now let me write it. M L power minus 1 T power minus 1. Density, mass upon volume, M L power minus 3. Diameter, okay, rho I am using, D for diameter, that is length, L. And velocity, L T power minus 1. Okay, so let me form an equation. Velocity is proportional to or equal to a constant K into rho into eta into diameter D power A power B power C, it depends on. So let me substitute now. L T power minus 1 is equal to, M is not there, so M power 0, L power 1, I can keep it, 1L is there. Next, K constant, let it be as it is. Rho density, M L power minus 3 power A, whole power A. Second, eta, coefficient of viscosity, M L power minus 1 T power minus 1, the whole power B. Fine. Next, diameter of the tube which you have taken, L power C, diameter power C. Now let us expand it, right? M power 0, L power 1, T power minus 1 is equal to the constant K. Now let us open it up. M power A, L power minus 3A, M power B, L power minus B, T power minus B, L power C. Fine. Now let us combine the terms together. M power 0, L power 1, T power minus 1 is equal to K into M. M power A plus B. Next, L power minus 3A minus B plus C. So L, 3 terms have come. Then T power minus B. Okay, now we have to compare the powers of M, L, T. Fine. Now, let me write comparing the powers of M, L and T. Mn and Lp. Okay. So 0, A plus B. A plus B is equal to 0. Next, minus 3A plus, minus B plus C is equal to 1. Last, minus B is equal to minus 1. Minus minus goes, B is equal to 1. We got one value. So let me erase this part and solve it here. Fine. Now I can substitute here A plus B. A plus 1 is equal to 0, which implies that A is equal to minus 1. Okay, let us put it in a box. Now this equation is there. Minus 3 into minus 1 minus B value is 1 and plus C is equal to 1. Minus of minus, so 3 minus 1 plus C is equal to 1. 2 plus C is equal to 1. C is equal to 1 minus 2 minus 1. So we got C value also. Let us substitute the values of all that. V is equal to K into, fine, rho. A is how much? Minus 1, right? Rho power minus 1. Eta power B is 1. So eta power 1. And D, diameter, C value is minus 1. Okay, so I can write V is equal to constant K into 1 is there, eta upon rho comes and D comes here. Okay, now experimentally K is equal to 1 So we say V, which implies V is equal to eta upon rho d. This is the formula for critical velocity of the liquid flowing through a pipe. What are the factors you see? Now I have got here V is equal to rho eta upon rho d. Okay, this constant is not 1 actually. This constant is having a value, and that is called R. That constant is called R, and what is R? R is called Reynolds number. Reynolds. Have you heard about in those days, in starting of ball pen time? Yeah, let me take the ball pen and show you. In the starting of ball pen time, we used to have a company called Reynolds. After that, Adgel came, GM ball pen, different ball pens, Roto, then Cello, See, Reynolds. First, let me write the word, then you will catch it. Fine. Then you will understand how these are all interrelated together and how it is relevant, how it is having application in our everyday life. That also we need to understand. Yeah, we are all night blindly solving some equation, right? So I am going to write the equation. Critical velocity is equal to R eta upon rho d, where R is called Reynolds number. Okay, Reynolds number. This Reynolds was a man who found that for a ball pen, earlier we had ink pen, after that gel pen came. Now basically, when you talk about the ball pen, you see, it is having we are having a tube here, right? You can assume it to be a tube. Inside what is that? Ink is there. But the ink is having particular viscosity, particular density. Liquid friction, okay, density, that is how much heavy or lighter, and the diameter. All this decides the smooth flow of the liquid in the refill, right? Refill, you can take it, throw it and put another refill in it. So you see here, this is a tube, right? You see what an invention it is actually. Yeah. Till then we were using ink pen, our hands and all used to get dirty. We used to have an ink pot and take a filler, and then with that we used to put the ink, China pen, fala like that. But now ball pen is very, very easy, and also you have gel pen where the liquidity is a little bit more. In this it is a little bit molten state, you can say semi-solid state. It does not leak and all these things. These are all scientific science to technology, right? This was a man by name Reynolds actually. Yeah, that's why the pen was called Reynolds pen. Now, what is R actually from this? R is equal to rho V d upon eta. This is called Reynolds number formula. Rho, density of the liquid. So the ink we have taken, what should be its density? V, with what velocity it should flow so that it will have a smooth flow. D, what should be the diameter of the tube? Dear students, if you are a little bit observing, it will be written 0.5 mm. Okay, that means its diameter. Nowadays, you are having MCQs, which you are using, what is that sheet? OMR sheet. OMR sheet having a different black pen. And you see what is the thickness of that? It will be written 1.0. Yes, the diameter is more. It can flow better. So you can fill 1, 2, 3, A, B, C, D is there. This will be a little sharper. So if you use that quickly, you can, circle the number. So that is used in QMR sheets and all. That is also having a different thickness. And you want very sharp. Pilot pen, you see, it will be having very narrow, 0.1 I think. Thickness goes on decreasing, the tip thickness also, right? So I am talking to you about the refill, the thing of it. So what are the factors? The density of the liquid, The critical velocity, if it exceeds the critical velocity, the flow will not be what you will say, streamline or steady, it will become turbulent. Okay, I'll tell you the values. D, diameter of the tube, and rho, eta, the coefficient of viscosity. Now, 0 to 2000, if the Reynolds number value is 0 to 2000, then the flow will be streamline or steady flow. If the Reynolds number is greater than 3000, then the flow will be turbulent flow. And if the flow is in between, Reynolds number is in between 2000 to 3000, in between the value the Reynolds number comes to be, then the flow can be streamline or turbulent. It will get vice versa change. Sometimes streamline and turbulent to streamline, it can be, that is happening in this range. So these are the application and uses, the way in which we can use the concept of physics in our everyday life. That's why physics is very interesting. Maybe it looks so hard because you should be more focused, and you should focus very clearly and understand the concept, comprehend it, and then practice it. Then physics becomes easy. I'm going to wind up this video with one small point here to say that Reynolds number is a dimensionless quantity. It does not have a dimension. How is it? Okay. What is the rho? Density m L power minus 3. Velocity L T power minus 1. Density L, again, diameter, keep it in mind, divided by eta m L power minus 1 T power minus 1. That is equal to m, only one m is there, L power minus 3, 1 plus 1, 2, minus 3 plus 2, L power minus 1, T power minus 1 upon m L power minus 1 T power minus 1. So you have 1 upon 1. So you have m power 0, L power 0, T power 0. This is nothing but no dimension. It is a dimensionless quantity. Dear students, I hope you enjoy this learning of these concepts, and have doubts, you ask me, and you can put it in your comment section. And thank you. Have a wonderful day.